Sense.
Yep, we're recording.
Cool. So yeah, today's dev session, we have two things on the agenda. We focus on one first and see how far we get. First one is around state think, design choices, trade-offs, and probably what we want to change there. And then if we have time, ABCI changes later. So Bucky, you want to give us the rundown around, like build up some context around the current state, the issues we're facing, and what we see as room for improvement going forward, I guess.
Sure. Yeah. So the basic challenge here is, we build up this blockchain over time. The blocks, the chain itself gets quite big and takes a long time to sync. And so we want people to just be able to sync the latest state of their application without having to worry about the whole history of transactions. And there's a lot of, there's a bunch of subtlety around what states people will keep and what state they're syncing to. And, once they sync up to a state, they'll probably need to use the blockchain reactor to fast sync the blocks from that state up to the current state. So the blockchain reactor is still going to be, important as part of this. And so the refactoring that's currently ongoing is, at least for the blockchain reactor, is still going to play a role here. But then the question is, okay, how do we actually design the state sync? Because we want to be able to support syncing basically an arbitrary Merkle tree. We more or less assume that the application keeps its state in some kind of a tree or another, or some data structure ultimately, and that basically some authenticated data structure, so that when peers are downloading pieces of it at a time, they can authenticate those pieces as they go. And basically, the kind of key parameter, I guess, is in the design is like how aware Tendermint is about the structure of the authenticated state tree or the authenticated data structure, right? And so, it could be kind of completely ignorant and agnostic to it, in which case it's just, the pieces are just arbitrary blobs, or we could have it know more and more about like the substructure and try to use this kind of like generalized way of describing paths through Merkle trees or something like this. And so, in the former case, if it's just kind of arbitrary blobs, then presumably that would lead to a simpler design, at least on the Tendermint side. You have some number of blobs you need to sync, and peers, you just request the blobs. Each blob has an ID, like a number or something, and then so it would be kind of very similar to the way the blockchain reactor works for the fast sync. You have a number of blocks, and you just sync the blocks, and the blocks are kind of self-contained, and they have a proof, and so we could do the same thing here. But the challenge with that is that for the tree, like, so say you're an application and you store your state in a Merkle tree, you have to know kind of for the whole tree how to chunk it up into some number of parts that you can then give to Tendermint to do the state sync. And so, like the kind of naive thing would be to like upfront serialize your whole tree, and then cut it up into pieces, and then you can start giving Tendermint those pieces. And so, is the simplicity we would get out of this on the Tendermint side worth the complexity that we might have on the application side for chunking up the trees? And we kind of need to address this question of how complex would it actually be to do this on the application side? And would you need to serialize the whole tree at once, or could you kind of figure out how big it's going to be ahead of time? Questions like this. And then kind of the other approach would be to basically, instead of just chunking up the tree and having some number of opaque pieces that we're trying to sync, Tendermint would be more aware of kind of the structure of the tree and would be able to request more specific pieces about what it needs from the tree. And so that instead of just syncing like arbitrary blobs, it could say, I want this range of keys, or, give me this layer, from this side of the tree. And it would kind of be more of there'd be a lot more structure in the requests. And, so that would reduce the burden on the application to have serialized the tree up front. It would just have to respond to those quests. Oh, you're asking for this part of the tree. Here it is. But it would put a lot more, that would put a lot more burden on Tendermint to actually incorporate, how to decide how to traverse the tree in the state sync. And, we would have to use some generalized Merkle tree query and structure description format, which we sort of have a prototype for, but, it's unclear exactly how mature that is, and so on.
So okay, so to rehash, what we want to be able is to sync arbitrary Merkle trees. Is that correct?
Uh-huh.
And sync from a last known state to a current state. Is that also correct?
We want to be able to sync arbitrary Merkle trees at some particular time.
Yeah.
And then once we have synced the Merkle tree, then we can download all the blocks that came after that time in using the fast sync. And that way we don't have to sync the entire history. We just sync, we sync the state from, maybe it's from 5 days ago, and then we run 5 days worth of blockchain reactor rather than, 2 months of blockchain reactor.
Yeah. And the motivation is to reduce resource overhead.
And sync time.
Okay. Yeah.
Actually, just I was trying to look a bit at the prior work with respect to this problem, and there are not many of research papers explaining this part of the state machine application. In most of the papers, state sync or in general, durability aspect is ignored. However,
in general, what?
In general, they ignore the durability aspect, like the persisting data.
Durability. Yeah.
So this is because it was somehow easier to publish a paper with, higher throughput, lower latency results. And if disk interfere, writing to disk interfere, then, this has a normally bad effect. And, but there is a very nice paper. I published it in the core channel, and maybe we can also put link here from BFT Smart guys, actually the guys behind BFT Smart, where they—
Can you reshare it in the core Tendermint channel?
In the core,
I can put it in notes.
Yeah, you can put it as a notes. I think.
Yeah, but can you reshare it?
Yes. So I put it here again in the channel, and then please just put it where you want. Yeah. And so they analyze this for still much simpler scenario than what we have. Like they assume BFT state machine application, but they don't consider like a large number of nodes, gossip, etc. So for us, it's much more complex. But still, it's very interesting just to see how some of those design choices affect negatively people. And it can like dramatically decrease performance of overall system, because like we are not doing this somehow orthogonal to the processing of or normal processing. So this is something which should happen as part of the normal processing. So like the state sync node is helping someone to fast sync, but also proceed in adding extending the blockchain. And so there are a few important things we need to clarify before we probably go deeper in design choices. First one is when the application is doing these snapshots, because like they have shown that if they are doing it in a synchronous way, like for example every k blocks, that this essentially block the blockchain itself, if you want, during this period of time, because you need either to pause the application while you're doing this, or you need a much more complex, like for example, copy on write semantics, which is again responsibility of application. So we are kind of increasing complexity on the API.
But that's basically what we already have and expect from stateful Merkle trees, right?
This is a good point. So I was not aware of this.
Yeah.
So essentially, because what they propose there is that you don't do essentially this synchronous snapshot, but you do it more or less. They kind of were proposing some some deterministic schedule so that there are always enough nodes being available for consensus. So in Tendermint, we are assuming that application is essentially, can you explain? Because I'm not sure I understand this.
Well, so, I mean, Tendermint doesn't make many assumptions really at all about how the application is managing its state. It does suggest that the application keeps its state in an authenticated data structure and that it returns the, authenticated fingerprint, like the root hash, with every call to commit, like ABCI commit, or I think we were talking about calling that state commit or something. And so, when you think about authenticated data structures these days and storing state in an authenticated data structure, you tend to, you almost tend to always kind of be thinking about a copy on write style data structure where you don't have to like recompute the whole thing every time. You just kind of, whatever changes, you add that and the old things are still there. And then you have some other routine to go and clean it up. Right. And so that's kind of the case with the AVL tree. I mean, it's called an IAVL tree, the I being immutable, because you don't actually change anything. You only add new nodes. So the old state is always there unless you go and explicitly clean it up, right? And so there's all this complex like orphan tracking and garbage collection logic in there so that you can clean up nodes that no longer have references from the current state.
Okay, so somehow we are assuming that for every height, essentially, we are having a snapshot.
Basically, yes. I mean, we're not really assuming it or relying on it, but that, if we're talking about building if we're talking about building a state sync module into Tendermint, and we want to, we want that thing to work in general, kind of without too many assumptions about what's happening on the application side. But I think if you want to consider the high performance case, then, Tendermint will assume that you're doing something, you're doing this intelligently on the application side. For instance, you have a copy on write data structure. And so you don't have to like synchronously stop the world to create your snapshot. Now, if you do, that shouldn't be a problem for Tendermint. It should just, it would slow things down. And so it's not optimal, but yeah. Does that make sense?
Yeah, it makes sense. It's just that it seems that we are assuming that the snapshots are being done synchronously, in a sense that like at each period could be number of blocks or something like this, that every node in a system is making a snapshot. Now, how it would do it, whether it would block the service or not, we are making such assumption.
Yeah.
Okay.
So there would definitely need to be some kind of configuration around how often your state snapshot changes, right?
Yeah, because like if you don't make such assumption, then it's more complex to do a cooperative state sync. Like
it's more complex to do what?
A cooperative state sync, like
like. Oh
this.
yeah. Of course.
Because people are having different snapshots, so then
you have no idea what pieces they have.
Exactly. So it seems that I think both those designs are assuming that every node in a system is having the same snapshot.
Yeah, I took that for granted. I don't know how we would possibly do this otherwise.
Yeah, because like for example in DFT Smart, but this is different system. They are just downloading by cooperative. In their case, they mean that you download the block from a single peer, and then you use other peer just to verify the correctness of the state.
Mm-hmm. You mean state? They download the state from one peer, and then you use others to verify it.
Exactly.
Yeah. And so that's not tenable.
Yeah, I think in our case we don't want this. So we want to do a cooperative distributed fast sync, and for this we need every node have the same snapshot. I think this is the requirement. And then they are saying that serializing the state, they were doing this with 1 gigabyte of state, the application.
Yeah.
Is pretty complex operation, and that this is essentially the blocking the progress of the system during this period, and then they were how they were fixing this. I forgot how they actually, they have some proposal how they can avoid doing this upfront serialization of the whole state. But I forgot how they do it. But they just have experiments which shows that if you have a state of 1 gigabyte and you need to serialize the state during the just doing state snapshotting, just during this snapshotting thing, that this could has a strong effect on the performance of the system.
Yeah. So I think so, and so that's basically that seems to be kind of the key concern for us too. That's surfacing here is, do we serialize the state and chunk it and send the chunks and have it be like opaque to Tendermint, so that all Tendermint has to worry about is which chunk number is being requested, or do we have a more aware, have Tendermint be more aware of the substructure of the Merkle tree and how much of it has been synced, and be able to make, queries for parts of the tree and subtrees and ranges and so on, which would avoid needing to serialize it on the application side. And it would just be, the application would just be responding to normal queries for parts of the state tree. And so this is kind of what we need to figure out. And
although even in the other case, when you are asking for just ranges of the tree, is it really like always more efficient? Because you need to download, you need basically to pull from the disk different parts of the tree.
Yeah.
So if people are asking you for different parts, you will not be able to kind of cache this maybe very efficiently, and so this also might be effect. So.
Yeah, that's a good point. So I don't know necessarily that it would be more efficient. It would, in theory, it would avoid the stop the world, serialize the whole tree step. But the benefit of if you serialize the whole tree and sync it, serialize the whole tree and chunk it, then you have all the pieces, and you can cache them and whatever too. And there's only so many, and all the peers are requesting, exactly what pieces. There's no kind of variability. Whereas in the other method, different peers might end up requesting different parts of the tree at different times and whatever. And so that you could end up where no peer makes the same set of requests to assemble the whole tree.
The first design choice, there is also an additional problem here. If people are, so now you have many peers, like potentially, and they must be asking you for a different snapshot. Like, could this happen? Or they're always asking you for the kind of last snapshot?
I think what we want there to be a latest snapshot that is associated with, we want there to be a latest snapshot. It could get tricky because the snapshot could change in the midst, the latest snapshot could change in the midst of someone trying to fast sync it, right? So we might actually need a few valid snapshots or something, or to just have a really bad experience for the syncer in this kind of changeover case. But ideally, like, you connect to the network, you connect all the peers, you find out what, you'd get like a proof for the latest state, like you do the light client proof for the latest state. And then based on that, you should know what the latest available snapshot should be. And then you can start requesting that snapshot.
Yeah, but like, what if you connect to 10 peers and only one of them is having the latest snapshot and all other guys are two snapshot behind, or one snapshot behind? Isn't like, maybe then it's kind of, you give a peer possibility to pick which one it wants to download, because it's more efficient to download from 10 people parts than just from a single guy to get a whole state.
Yeah.
But this would require then keeping multiple snapshots, multiple kind of active, but this means that you have like a lot of burden on the memory, because you now need to keep in memory after you serialize this thing, or maybe to disk. I don't know like how we imagine this to happen, but like it seems for me that we can't really avoid having multiple snapshots, and so the fact that we are serializing is not just once, but it might actually be it might have additional overhead.
Yeah, I mean, I could imagine us only having one. It does mean that people trying to sync at the edge might end up getting screwed, and we would have to there would be some synchrony assumption that you can actually complete the sync before the next snapshot is supposed to happen. And if you don't, you'd kind of get screwed. I mean, we could obviously improve that by keeping the last two or something like this. But unless we're going to keep all of them, then kind of in the worst case, the user is, that actually might not be so terrible. If we keep all of them and keep them on disk and, for instance, just cache the latest one in memory or something, and then users would never get screwed when they're syncing.
Yeah, this might make sense. And so in the second option, where we have a more kind of intelligent fast sync, if I understand correctly, we don't need to keep really snapshots on disk. We just have the data structure itself doing it for us. And so
yeah. So I mean, you still need a snapshot, i.e., you need to know what the state is at a given time and have it, persistent. But you don't need to serialize the tree and chunk it.
But like the fact that you know what was the state at particular point in time, this is something which is provided by the data structure itself. Because
it's supposed to be, yeah. Like, I mean, the AVL tree we use kind of already does that. By default, if you don't do anything else, it keeps the state from every point in history. And so you can query historical state and get proofs and everything.
Can I intervene at this point?
Sure.
Because it sounds like we have some intuition, but it also sounds like it would be nice to gather more evidence around this, especially like what kind of algorithms would there for this chunking, if I understand correctly. But the thing that I would like to focus on a bit is more the app side of things, right? Because this will have potentially very large usability implications if every app is required to have a notion of this and what a chunk of a tree is and so on, right? Unless I misunderstood the two potential approaches, where the naive one is more involved for the app and the other one is more involved for Tendermint.
No, you're very right. This is a very valid concern. And they're also talking about this in the paper, that in the other case, you are actually, the API essentially is much more complex, or writing application is much more complex.
Yeah. So, for example, like syncing in general is never exposed to the API to the ABCI at the moment, right? Like the app doesn't know that, for example, the blockchain is syncing behind the background, behind the scenes. Like in general, like one of the things like is, do we have some form of guidance? Like what is it really that we want ever to bubble up, right? Like what kind of physicality, if you will, or what kind of notion should the app really have besides the life cycle of a block, for example, which seems to be core of the ABCI, if I understand correctly. Yeah. So would it go against actually what we try to achieve with the ABCI if you have something more infrastructural that you have to cover?
Interesting.
And also like to the next extent, will it be optional? Like, can you provide the primitives to chunk your states, or will you always have to do that? And that means that even an example app has to satisfy those interfaces.
No, I mean, I think I think state sync will always be optional. So we're never going to require anyone to do it. It will be like an optional component of the ABCI, because insofar as it's going to require new ABCI messages, you'll still be able to run a ABCI app even if you don't implement those. So, we'll need to figure out exactly what that looks like, but I don't think that's too hard. But with respect to, I mean, you're right that currently there's kind of no awareness at the ABCI level of where the block came from. It's just like, here's a block and process the block. And this is something that, I think a few people have actually asked for. There's an open issue for it. That's like, alert the ABCI when we stop fast syncing. But maybe what we actually want to do is include some kind of flag or something in the begin block, or to somehow indicate, how we actually received this block, whether it came from fast sync, or whether it came from the consensus, or whether, we're just replaying it from disk or something like that. And maybe there's other modes. So that might be a simple way to address that. But then with the state sync, basically, I mean, I've kind of just been thinking of it as an extension of the existing query interface. And the query interface already kind of imposes this Merkle tree, like general Merkle proof structure, and basically says that, okay, you can make queries and you can have arbitrary queries. And if you want to return proofs for your queries, those proofs kind of follow this very generic form for authenticated data structures of like basically linked components where each component has somewhat of a self-contained proof that connects to the next one. And so that's already kind of in there. And, so people don't have to use that if they don't want to provide proofs, but if they do want to provide proofs, then they would be using that. And so the state sync, if it were to just use the query system, then anyone who is providing proofs would already kind of be hooked up. And then Tendermint could just be using the query calls to get whatever parts of the tree it needs to send to the peers. But that would be, it'd be a little bit different to do the kind of chunking thing, which expects you to support a different kind of query into the tree, which is a little bit lower level, which doesn't really reflect the structure of the tree in the same way. Maybe it does. I mean, this is kind of an interesting thing to think about, like alternative ways to query parts of the tree where you're not really querying for a key per se, but more so like a piece of the tree or a middle chunk of the tree or whatever.
What is missing? Because you talk about this in a high potential way. Like, do we need to gather more evidence that there are certain data structures or certain ways to build this, to have this built out easily? Because it seems like we have some intuition, but not really hard evidence. Or like, for example, the paper that Zako shared. Is there more research in that direction? Like, what are actual next things to like funnel down the conversation more into the direction where we can actually make a choice of which route we want to go to, or are better informed to say what is the more sane way to go forward with it?
Mm-hmm.
I'm wondering, Bucky, can you just explain the query side? I understand, but there is in FastSync we need to install a new state, and for this we definitely need a new ABCI call, I guess.
Mm-hmm. Yeah, that's right. So in my latest thinking, in the comments I left on Akratos's first take at this, let me pull those up. Basically, I was proposing that we would only really need one new ABCI message, and I believe that was like a set state chunk or something like that. What did I call it? Write recovery chunk. And then everything else would basically be happening through the query. Now, they raised some concern that, because the query shares a lock, and so it might actually be pretty slow. And so, we would have to look into the concurrency of accessing that state. But otherwise, I mean, at least from a theoretical sense, we're basically talking about adding one new method to the ABCI that allows you to actually, write directly to the state. And to just like build the state up like that. So unlike currently we have things like deliver TX, which is like, deliver a transaction and execute it, and the result of executing it will update the state. And so here is a different kind of ABCI message to change the state of your application, which is a little bit more surgical and low level. And it's like here it's not really it's not part of a state machine. It's not really state machine transition functions. It's more like you're just actually writing directly to the state. So in that sense, it's kind of, going back to what Alex was asking a little earlier, like in that sense, it's kind of a different way of thinking about ABCI compared to how ABCI like currently works as like, mostly focused on like state machine transitions. But given that there is state and we need to sync state, and ABCI already supports this idea of like multiple connections with distinct, concurrently managed states and so on. I don't think it's too much of a stretch to add this through I don't know how else we would do it besides really through ABCI to actually I can think of a few ways. We can talk about those in a second, but you would set up a new ABCI connection and then offer this new method that allows you basically to write something directly to the state.
But is it really the state sync a kind of optional thing, or it's really somehow core part of the state machine application system?
Well, I think it's optional because at least in theory, you can always just run the whole history of the blockchain, right?
You cannot, because like with the rate we are creating block, it's not realistic. Like you will get out of the space pretty fast.
Well, yes. I mean, in theory, you'll eventually catch up. It's possible the blockchain gets to a point where it advances faster than you can sync, so that you'll actually never be able to sync it. People have speculated that like that's happening to Bitcoin and stuff, or that it will down the road. But some applications might use like the no empty blocks thing, or certain other things, or they'll dump state and restart. There's also like out of band state sync that you could do, where you just like if you have a copy of the database, then you can just like rsync it to someone, or if you have SSH access, or if you use a BitTorrent file or something like this, right? So I'm pretty sure there's a BitTorrent file for a big chunk of the Bitcoin blockchain, so you can just download it using BitTorrent. But I don't, I think we want to provide something in band, and then most serious production users are probably going to need to support state sync. Yeah.
But as sort of a weird orthogonal question, why has no one actually integrated the BitTorrent protocol, which seems like it's very good at this application, as state sync, and then have like some sort of commit verification for the final hash, just integrated into a client?
You mean just like implement the BitTorrent protocol for doing this?
Yeah, it's available as a library. I don't know if it's available in Go, but certainly for like some clients.
Well, there's a lot of we probably could. I mean, I think it has a lot of dependencies on other pieces of the BitTorrent ecosystem, like the existence of a torrent file and the BitTorrent encoding that it uses, and there's a lot of things now. There's like tracker stuff, so either you expect to have a tracker or you expect to have a DHT, and we don't really satisfy either of those. So it might be quite a bit of work to like integrate an existing BitTorrent library into the stack, compared to just like re-implementing roughly the same, tit for tat style protocol, or whatever they actually use for swapping pieces.
Okay.
I'm just wondering whether here we need, with the API, to more or less be clear with the application developer that they do have a think about they need to think about the state sync, and it might affect the overall performance significantly if done in a not optimal way. And if you don't have this clear, as part of the API and with query, I'm also wondering whether we are kind of hiding this to some extent. And this, I'm not kind of fully convinced that it's really good idea. Because
like to hide it, you mean? You basically want to make it mandatory. Everyone, exactly. If you're building an app, yeah.
Exactly. And so I would kind of want to have.
Who's got the dog?
Yeah, it's me. Sorry, fucking plebs outside.
As simple as like possible API. I think this would be nice, but that we don't hide this. That we more or less are telling application developer, you need to think about this thing, and it might affect significantly the overall performance, and maybe even have some kind of guideline there. Because like if you look at these experiments number, then you see that like more or less if done in an not optimal way, the throughput goes to zero essentially during some period of time, because you're not doing anything useful. And so
I mean, given that we have concurrency on the machines, I don't think the throughput would ever go to zero. You could still do things while you're building up your state snapshot or whatever. But I mean, I hear your point that you want application developers to think about this. But so I guess I think about it, from I think you're probably right. And in the same way that, there's already durability stuff in ABCI, like through the info message, right? So you kind of, in a sense, it's also kind of hidden. You can kind of be like, well, the only thing you actually have to implement is deliver TX, and like nothing else really matters, and then even if you don't persist your state application side, then when you restart, Tendermint will just replay everything it knows about, and like you can get away with that, and that's fine. And from a developer accessibility perspective and like making it easy to get started, I think we want to preserve this kind of, you don't have to think about much to just get something started and see it working. But when you get into, oh, now you want to run a production deployment and, you know, you want it to be performant and you want new people to be able to join and so on. Well, now you have to really consider durability, and there are multiple dimensions to it. One is, you know, what happens when a node shuts down and comes back? Well, it should have persisted its state, and it should tell Tendermint what the latest state it knows about is. So Tendermint doesn't have to replay anything. And then, you know, oh, if you're bringing up a new node, it needs to be able to sync a whole state, which means you have to be able to comply with the state sync thing. So I think, I think from that perspective, we don't want to hide it, but we still want to make the initial experience, you know, for a developer coming to ABCI, like I think reasonably lightweight. But you're right, we shouldn't hide it, and we should make sure the like durability story is like well documented and well accessible.
Also, like here we are making.
But we could also.
Go ahead, Alex.
We could also make the case that we should educate early on to not have people surprised later down the road, right? That's always a trade-off that we can make.
Yeah.
But when we talk about developer experience, maybe we can focus a bit on like an impact we directly know and can assess, which is the SDK, right? And Cosmos in general. Because you mentioned early on that changes here will definitely impact that. So maybe we can explore a bit what it would mean if we change things around and how it would impact the SDK and the Cosmos Hub. To have an actual use case to talk along.
Yeah. So the other thing, so basically, you know, and this would kind of contradict what I just said, which is that in reality, we're actually not expecting the average developer user to actually have to see the ABCI. Really what we're expecting is a small number of, you know, ABCI experts to build frameworks like the SDK, and for the average user to have to see the SDK. So from that perspective, you know, all of this stuff should just be front and center in the ABCI, and the person coming to ABCI is mature enough and is expecting something, you know, advanced enough to know that they're going to have to think about concerns like durability and state sync and so on. So
very valid point.
So from that perspective,
like your first blockchain, your first blockchain app is not what we should optimize for something like the ABCI, right? Like this is also like something that we should crystallize more and more. Like, is the ABCI a power tool, or is it something that is to get people have it an approachable thing, right? But if there is the SDK already, which satisfies their needs, that could mean that we could be more more advanced in the ABCI. Okay, sorry, I interrupted.
No, so I think, and I'm still kind of getting used to that, because, you know, when we originally wrote the Tendermint documentation and site that is still available, it was kind of designed as like, you know, you're writing your first blockchain application, you can do it on Tendermint, and, you know, you just have to know a few things about the ABCI. But I think probably we actually want to get away from that and instruct, you know, if you're trying to build your first application, you should go to the Cosmos SDK or Lotion or, you know, any of these other frameworks where people who do understand ABCI have already done a lot of work for you. And then we can probably re-architect a lot of that Tendermint documentation to be geared more specifically towards people who are not just trying to write an application, but who are writing an application framework, right? And I think that would actually resolve a lot of tension and confusion and so on, and would probably improve our docs tremendously and make them clearer and maybe less verbose and so on. So
I couldn't agree more. It would like relieve the tension of those two forces, right, in ABCI development.
So that's an important point.
So with the SDK, more specifically to the SDK and Cosmos.
So the point is, for an application developer using the SDK, they won't even notice, right? I mean, that's the idea, is that nothing they do will be impacted by us updating the SDK to support state sync. It'll happen completely under the hood in the store package, which the developer doesn't touch or think about. They have an interface to a store, and they don't have to worry about it. Right now, the SDK only supports the AVL tree. Maybe in the future it'll support other trees, so it'll have to implement whatever kind of state sync thing for each of those trees. But that's a concern for the person, you know, for the SDK developers themselves who are, you know, managing state, not for the application developers who are using the SDK. As far as I can tell, they won't be impacted by this at all, except for maybe, you know, a performance concern here or there or something. Does that sound right? Am I missing anything, like Chris or anyone else? Like, I don't really see how state sync would impact an app developer.
That sounds right to me. I mean, I guess it would be helpful if they at least know that it's going on, so they have some idea of, like, at the moment it's easy to persist things that you shouldn't really be persisting, but that's more of a general concern,
Right.
regardless of whether state is being synced. I don't think it will change that much. Like, anything you ought to have done anyway, you should also do when there's state sync going on. So.
Right. Yeah, so I think it'll all be happening under the hood at this kind of ABCI layer. That is the business of the people building the frameworks, not the people building the applications.
I think that's a major takeaway, and I think that's something we should definitely capture somewhere, like this understanding of the ABCI being a power tool and how it could influence our decision making going forward. Yeah. And as we're approaching the end of our session, would like to discuss quickly what concrete things we want to do as follow-ups to like have at least the conversation going in the right direction, and all under the premise of finding ways to make the blockchain more optimized, I guess, going forward. So less resource intense, and to circumvent some of the issues we see rising with increased blockchain size. So yeah, like something where we at least have a proper proposal or some.
Yeah. So I think there's basically two kind of open things to think about that are that represent kind of the two approaches that we might take here. So the one thing is, if we're going with this chunking approach, I think we need to actually try to understand what it would look like and what the impact would be. So, is it feasible to serialize the whole tree and then chunk it and then call it a day? Is that, are there opportunities to chunk the tree kind of just in time so that you don't have to serialize the whole thing, but you can kind of figure out how many chunks there are going to be and how to create them sort of algorithmically, given that some global details about the structure of the tree, like questions like this. And if all of that, if the answers to that are kind of like positive, then I think that would be a strong signal to go in that direction because of how simple it'll be on the Tendermint side and how much it will mirror the existing blockchain reactor. And then the other side is like, okay, if we are going to do this more query-based thing, I think we need to have a better idea of what the actual algorithm would look like on the peer-to-peer side for how to query through the tree and how to get the pieces you need to actually sync the whole tree, and what that would look like and how we would determine it and so on. So those are kind of the open questions for the two sides of the coin, for the two sides of how we might design this. One, how are you actually going to serialize the tree, and do you have to do it up front or can you do it in real time? And then the other is what is the actual strategy for syncing a tree that isn't just serialized into chunks, but for which you actually have to request parts of it. And with the latter, it would really bring this whole general Merkle proof system kind of to the forefront, which might not be, it might be a good thing in the sense that we need that for IBC and it's already part of the ABCI proof system. And so, to have more people thinking about it and so on, but it also, is probably going to make it more complex to implement on the Tendermint side. And, maybe that thing is still evolving. And so, yeah, so I'm not sure in summary.
One question about like the requirement on Tendermint. When application is making a snapshot, do we assume that Tendermint on its own will also keep these snapshots? At least some of them.
I think so, yeah.
Because I guess we need to do this because right now, if when we reset the node and the application itself, we keep the whole blockchain. So basically, that's why we can always recover this. If we switch to a model where we have a snapshots and we are removing part of the blockchain, then we need at the Tendermint side to also keep snapshot to have the same guarantee to the user.
Yeah. I think the assumption we would make is that, say we snapshot every 50,000 blocks and then you keep all your snapshots. And then, that should, I would think, even if you have to keep a copy of the snapshot and serialize the whole thing and store it on disk, that there would still be tremendous savings compared to storing all those blocks.
But these snapshots are not the one used in FastSync. At least if we talk about this letter option, there we are interactively talking with the application during FastSync. So the snapshot.
It would be. It's just that you didn't have to serialize it. You just keep it in the form that it was in. You just don't garbage collect it, right?
Okay.
Yeah.
All right, we kind of have to wrap up. Baxter, the points that you saw or that you see, like the two ways forwards and what it would entail, like capture an issue so we can disseminate that into more workable chunks.
Yeah.
Because it sounds like we have some research to do, but also come up with more tangible proposals so actually people understand the impact on the code base.
Yeah.
And then weigh in on a more like, what does it mean for Tendermint, and do we want that? Is that complexity that we could live with?
Right.
That I think that would be great next step.
Okay, I can write that up. Yeah.
Cool, and perfect. And for the ABCI changes, I think we just allocate next week's session, and then I mean it's a nice segue, even so there's a week in between because we already talked about ABCI and new understanding, and then make that center of the discussion next Thursday.
Okay, sounds good.
Cool. Thanks everyone for your time.
Everyone. Yeah. And we'll see you online.
Cool. Thanks, everyone.
Latest.